Okay, so I wanted us to look at this tutorial. So the thing here is that you guys are supposed to solve the tutorial sheet because the tutorial sheet is a student's activity. So ideally, you people are supposed to solve, and I'm just supposed to be seeing how you are solving and guiding you here and there. Okay, but then given the circumstances I think it would be very difficult for you to write, given that it is an online class. I'm going to help you with some problems, but then I think the other problems I still want to see how you guys are doing, because if you just watch me solve the questions, it might not be very, very helpful for you. Watching is quite different from solving. Okay, so just for the sake of today, and then the other thing that I wanted to say is that you know that now this online learning has to come to an end, because it is expected that full-time students are on site. So the only reason why we are still having this is because I think there was a lapse in the timetable. Someone hinted me that there was a change in the timetable schedule. So instead of us losing the time, I thought that we could use it to do something. Okay, so now for the sake of just one moment, I need to. Okay, so what I was saying is that for the sake of the people who are under distance, sorry, I think there is quite little that can be done, that we are now learning physical. Then I think maybe the best that could be done is that you could try to work together with the guys on full time, try and share some solutions here and there that we are having from the tutorials. Okay, before we get started, anything maybe that we can talk about, just under 3 minutes or so before we get started. Anything that you want to talk about? Yes, please.
Yes, sir. Just a question now, since we have that situation where now we'll be having the physical learning.
Yes.
What about us, the distance students? Are you going to be providing the modules or what?
Okay, so you know the way it is, it's quite tricky. The distance, the distance mode of study is different from the full time. So actually, for the distance, you have been joining in the class, just taking advantage of the fact that we are learning online. But the distance mode of study is slightly different from the full time, in that I think that the contact time is only restricted to the 2 weeks that we have. Okay, so yeah, basically that is what I can say. But just to help each other, maybe we can be sharing some of the things that we are doing in terms of just maybe the solutions. In terms of the solutions, you could we could share those things. But having a physical class like separately for you, that will be difficult. That will be difficult. Okay. That is, I think that is actually the more reason why just for this tutorial, I decided it to be online, so that because no tutorials are extremely important. So I decided that it be online so that you are also at least able to follow. So we are going to see if maybe in the future we could also arrange that, but you must know that it is against the school policy because we are no longer learning online.
Oh.
Okay. Anything else?
Oh. All right, sir.
Anything else? All right. So let us get started. Okay. So this is problem 1, I think, from your tutorial sheet 1, and then it reads the 3-point charges positive Q1, negative Q2, and positive Q3 are equally spaced along a line as shown in the figure below. So here I don't have a figure, but we can still produce that, that figure. Okay, so the question goes on to say, if the magnitude of Q1 and Q2 are equal, if the magnitudes of Q1 and Q2 are equal, find the magnitude of Q3, find the magnitude of Q3 such that the net force on Q1 is supposed to, I think the question is not complete, it's supposed to be so that the net force on Q1 is 0. So here it must, I think, say 0. Something like that. Okay, so let us try to see how we can solve this problem together. So I'm going to draw the coordinate system. I'm going to draw I'm going to draw these charges. So I have, this is my x-axis. Let's say this is my x-axis. And then these charges, I'm told that there is a charge that is here. Okay. Okay, just allow me to see if I can erase this. I hope that I won't. Okay. So let me say this is our charge. The first charge, there is another charge somewhere here. And then there is another charge somewhere here. All the charges are in the x-axis. I think if you recall very well, all the charges are in the x-axis. So you pardon me, instead of using the capital letter Q, I prefer using the small letter q, but that won't change anything. It's just a notation. I prefer that notation. Instead of using capital letter Q, I'll use the small letter Q. Okay, so I think if I'm not mistaken, my Q1 is this one, saying that this is Q1 and it is actually positive. And then this is Q2 and then it is negative. And then this is Q3. Okay. And it is positive. Then we are told that these are actually, equally separated. So if I say this Q1, so the question is that if the magnitude of Q1 and Q2 are equal, so we are saying that Q1, the magnitude of Q1 is equal to the magnitude of Q2. We can just say that it is equal to Q. Okay. And then what is the other thing that has been given? So find the magnitude of Q3 such that the net force, find the magnitude of Q3 such that the net force on Q1. So Q1, you can see that Q1 is basically our charge of interest. We want to find the forces that are acting on Q1. So they are saying that if the net force on Q1 is equal to 0, so the other data that we've been given is that the force on Q1 is equal to 0. That information has been given. Okay, so we have two pieces of information. Magnitude of Q1 is equal to the magnitude of Q2. The other thing is that the force on Q1 must be equal to 0. Okay, so the question is that what is your Q3? What is the Q3? That is what the question is asking. Before we go any further, any question before we proceed? Any question? Just the way we have set up the problem. So I believe that it is clear. So the next thing is that, you know, this is our charge of interest. Our charge of interest is Q1. So we have to indicate on this diagram what are the forces that are acting on Q1. What are the forces that are acting on Q1? So let us try to indicate that. So the first force that we have is a force in this direction. So we have a force in this direction. Can someone tell me this is a force due to what? To which charge? Is it the force due to, is it the force on Q1 due to Q2 or the force on Q1 due to Q3? Can someone tell me? This force that I've indicated, is it due to Q2 or due to Q3?
It's due to Q3.
It's due to Q3. Have you seen? The reason is very simple, because Q3 is positive. So it will be repelling. It will be repelling Q1. So the force will be in this direction. In a similar way, you can see that Q2 is negative. So it will be attracting. So the force due to Q2 will be in this direction. So what I wanted to say that this, you can say that this is the force on Q1 due to Q3. Okay, in a similar way, in a similar way, you can say that you have this one here, which you can say is the force on Q1 due to Q2. Okay, so the, I've represented all the forces that are acting on Q1. Okay, and you know that all these forces must cancel out, because ultimately the force must be equal to 0. But we'll come to that issue. The next thing that I want to say is that if I take the origin, let us say that I take my origin to be Q1. So I say that here x is equal to 0 at this point where Q1 is. And then at this Q2, I can say x is equal to r. Okay, since this is equal to 0, the distance from here to here is r. So then x is equal to r at this particular point where Q2 is. Okay, and then since the question has said that these charges are equally spaced, then at the point where Q3 is, I can say x is equal to 2r, because there's an additional r distance. So I'm calling this distance r, this distance r. So it means that from Q1, Q3 is at a distance of r. Okay, so just there I have some other pieces of information. I can say that I have R1, 2. Can someone tell me what is R1, 2 in this case? What is R1, 2? It is R. Because, you know, R, remember R, we denote it, we use it to denote the distance between the two charges that are exerting forces. Okay, so this R1, 2 is the distance between charge 1 and charge 2. I've said it's R. And then the other one is R1, 3. Because, you know, when calculating this force 1, 3, I'll need R1, 3, the distance between charge 1 and charge 3. When calculating this force 1, 2, I'll need this R1, 2. So this R1, 3 is nothing but 2R. Any question before we proceed? Any questions before we proceed? Okay, so it is very clear. Okay, so now let us now try to apply the principle of superposition. You remember the principle of superposition that we had learned? We said that if you have more than two charges exerting a force on any one charge, then the total force is basically a vector sum. The total force on that charge is actually the vector sum of the forces exerted due to all the individual charges. So in short, we are saying that F1, remember F1 is basically the net force, and we also know that this F1 should actually be equal to 0. So we are saying that F1 must be equal to the vector sum of F1, 2, and then plus F1, 3. So that is our equation. We are saying that F, the total force that is acting on Q1, is equal to the vector sum of the force due to Q2 and the force due to Q3. And then we have actually labeled those on the diagram. And now remember from Coulomb's law, the force is just given by K, right? Maybe let me just do this. I say that but Coulomb's law. What is this F12? F12 is just equal to the K. Remember, I have that K, which we all know that it is 1 over 4 pi epsilon naught. So this will be Q1 and Q2, and then over R12. You already know that R12 we have already indicated, so it is just nothing but. Now I must also state the direction. Is this in the positive x-axis or is in the negative x-axis? F1 to look at the diagram, is it in the positive x-axis or is in the negative x-axis?
Positive x-axis.
In the positive x-axis, so it's important to indicate that. So it's in the positive x-axis, so it will have a positive value. Okay, so this can be written as K Q1 Q2 over R squared. You know, this is, I'm using that, and then it's in the x-axis. Okay, so I'll say this is my first equation. Now in equation 1, you can note that don't make a mistake of including the negative here. Don't make the mistake of including the negative. You see, even if Q2 is a negative, I've just put it. I think there was someone who had asked the question when we are learning about these negatives. So that is where it becomes very important, because Coulomb's law only talks about the magnitudes of the charges. Okay, so the sign will come in when we are talking about the direction. I think that is important. Anyone who is not clear there? Anyone who is not clear why the sign here is not indicating there? Okay. So in a similar way, I can also write this F13. F13. Now you can see F13 is in the negative direction. So I'll indicate that negative, and then I'll say K, and then I'll say Q1. What are the forces that, what are the charges? There's Q1 and Q3. So Q1, Q3, and then over, what is the separation distance? The separation distance is basically 2R. 2R. Now don't forget to square it. Everything you must square it. Okay. So now, since you have these two equations, so this, maybe I can say that this is, I want this to be my equation. I want this to be my equation 1. So that this is my equation 2. And then this should be my equation 3. In equation 3, there's something that I need to put is the unit vector in the x-axis. So this negative, you can see, it signifies the fact that this is actually in the negative axis. Okay, so sorry class, just give me a minute. I've just received an important call that I need to attend to. Just okay, so sorry for that. I think it was just a pause. So in short, are we all together? Are we all here?
Yes, sir.
Yes, sir.
All right. Okay. So so I'm just going to say that I'm substituting this equation 2 and equation 3 into which equation? Into equation 1, because I'm applying superposition principle. So I'm saying that these are the forces, the net force on charge 1 must be equal to this K, and then Q1, Q2 over R squared, okay? And then there must also be plus. There's a minus. There's a minus, and then K, Q1, Q3 over 2R squared. Okay, all this must be in the x-axis, along the x-axis. Okay, so but from the information that you have been given, you know that the magnitude of Q1 must be equal to the magnitude of Q2. So I'll just represent it by Q. And also you know that the total force must actually be equal to 0. So these two pieces of information will help us a great deal. So I'm saying that here we say 0 must be equal to, there is a K that is here. Now Q1, Q2, it will just give me Q squared, and then over R squared, and then minus, I'll say K, and then this Q1, I'll just indicate it by Q, and then the Q3 is the one that I'm looking for. If I evaluate that, that will be 4R squared. Okay? Yes. Everything, if you like, it must be the x-axis. Okay, so since I have a 0 here, I can rearrange these things. I can say that K times Q times Q3 over 4 R squared must be equal to K Q squared over R squared, then times that. Yes, at that point, you see that these two can cancel out. A lot of things can actually cancel out there. This can cancel out. This can cancel out with one of that. And then this can actually cancel out. And straight away, you can see that Q3 will just be given as 4 times Q. Okay, and what does this mean? Remember, Q is just the same as Q1 or Q2. So we are saying that the Q3 must actually be equal to 4 times Q1, or it must be 4 times Q2. So in short, this is basically the condition that is required in order that the forces that are acting on charge 1 becomes equal to 0. So if you replace under Q3 here, you replace the 4 times Q1, which is actually a positive, then this charge here will remain at rest. It means that the attractive force that it is receiving from this will be equal to the repulsive force that it is receiving from this charge. Any questions? Any questions? Okay, so since there are no questions, let us go to the next question. But I think before we go to the next question, maybe let me end this session because it is almost now coming to an end. So let me end this session and I'll meet you on the other side where we try out another question. Okay, so I think we are set. Can we try out one more question? Can we try out one more question?
Okay.
The people who are coming will be joining us. Okay, so the question says that a point charge 2Q is, whenever we talk about the point charge, I prefer using the small letter. So whenever we talk about the point charge, I prefer using a small letter. So you pardon me that I'll be using the small letter, but that doesn't change the figure. If you want, you can use the capital letter as indicated. So the question says that a point charge 2Q is placed at the center of a square of side length 20 centimeters. 4 identical point charges Q are located at the corners of the square. So the scenario that we have is we have okay, so we have a square like that, and then we have some charges that are at the corners. We have some point charges that are at the corners. And then we are saying we also have another charge that is at the center. And our question has told us that at the corners we have Q, we have another Q. And then we have a Q here, then we have another Q here. And then at the center we have a charge of 2Q. We have a charge of 2Q. So now part A of the problem says that find the force on the charge at the center. Find the force on the charge at the center. So in short, this question, by the way, I think that, we have been given the side length. The side length is 20 centimeters. I don't like writing the numbers on a diagram, so I'll just write L, 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 L. And then I'll say L has been given to be 20 centimeters, which is basically 0.2 meters. So that is a smarter way of doing it. I don't write the numbers on the diagram. I just write the symbols, and then I write the value somewhere else. Okay, so the question is, part A of the problem is asking for the force on this charge here that is at the center. So the force on that 2Q charge. That is what the question is asking for. Okay, so maybe let me get some input from you. What do you think? How do we proceed? What will be the force on that charge at the center? Huh? Hello? Hello? Ladies and gentlemen, are we here? How do you calculate that force?
Yes, sir.
Yes, Mr. Mchemba, you want to say something?
Maybe it's 0, sir.
It will be 0. What is the reason?
I stand to be corrected, sir.
Yes, so why, yes, please, you're free to.
Since the charges on the corners are of equal magnitude.
Sir.
The charges at the corners are of equal magnitude. Okay, and so,
magnitude.
Mr. Mchelek.
And so they are cancelling each. They are cancelling each other, sir.
The forces are cancelling each other, and that is actually the correct, those answers that have been given are actually the correct answers. So you can see that what we have is that this force that is coming from here because the distance from here to here is the same. So we have the force in that direction, but again, we also have the force in that direction. So these two are actually cancelling. And secondly, we also have force in this direction. Then we also have the force in this direction. Pardon my drawing. So these two forces are also cancelling. So, so we are saying that this for part A, very simple. We don't even need to do any calculation. We can see that this is equal to 0. But then the reason is what is important. The reason, so such a situation where each charge has got a corresponding charge that cancels with it. What do we call it? So we say symmetry. So this is happening due to symmetry. You see that system has got symmetry. So we say this is a symmetric argument. We usually refer to as the symmetric argument. So just when you write this, it means that you explain everything. Because of the symmetry, you see these are it means that the forces are cancelling, and it means that also the electric field will be able to cancel out. That's just that. So typically, such questions will only have 2 marks. The first mark is for you to state that. The second mark is for you to explain the reason. Simple as that. Now we go to part B of the problem. Did I see a hand? Did I see a hand from someone? Okay, so let us now go to part B. Part B says that find the force on at the center if one of the charges at the corners. So now part B of the problem. Part B of the problem is saying that if one of the charges, so let me say that this charge is the one that has been removed. Let me assume this is the charge that has been removed. So since that charge has been removed, then even the force will be removed. Okay, even the force will not be there since the charge has been removed. So what I just want to do is that these two forces are still there, but then okay, so because of the symmetric argument, these two will be able to cancel out. So the force that we have will just be due to Q. The force that we have will just be due to one of the charges at the corners because these two charges are cancelling out. So the force that we have is just due to the charges at the corners. So the only thing that now that we have is to compute. We know that the force, this force on 2Q will now just be equal to K times times the product of the magnitudes of the charges. So the first charge is 2Q itself. And then the second charge is this Q. Then over R squared, where R is this distance from here to here. R. So this will not be cancelling out. I think I must remove, can I manage to just remove this? Yes. Okay, so the R is now this distance that is here. So now my question is, how do I express, anyway, before we proceed, anyone with a problem on just why we have written the equation like this? Anyone with a problem? Is it clear? Is it clear?
Yes, sir.
Okay, so then what
Yes, it's clear.
what we do is that what I was saying is that we just need to calculate this R, because what we have been given is L. So you see that R is just basically from here, from let me draw with a different pen so that you're able to see it clearly. So we are saying that this R is from here to here, and from here to here. You can see that it is making up a right angle triangle. So what is the distance from here to here? It is half L. From here to here is L. So it means that this is the midpoint. So this is half L. And then again, from here to here, it's also half L. So you use Pythagoras Theorem, then you know that R squared. You use Pythagoras Theorem, then R squared. R squared can just be given as half L squared plus, okay, I'll just say L over 2 squared, and then L over 2 squared. I think we have explained why we're having that. So it means that R Okay, so it seems that I had lost my connectivity, and as a result, I also lost my work. But I think you guys still have it. So where are we? We are just trying to say F2Q in that diagram that we had was just equal to K times 2Q, then times Q over R squared. We were in the process of finding what this R squared is. We said that this is L over 2 squared plus another L over 2 squared. And then if you try to work this one out, R squared is just basically L squared over 4 plus L squared over 4. And then if you evaluate, you work this one out very nicely, you just find that it is 2L squared over 4, which is just nothing but L squared over 2. Okay, so you are just substituting this. You want to substitute it back in this guy, you substitute it back there. Then this force from 2Q is just equal to K. And then have a 2 that was here, and Q squared. And then this R, since it's in the denominator, I can just reciprocate it. Then I have 2 over L squared. I hope we all understand. This R squared here is in the denominator. So if I want to put it in the numerator, then I'll have to reciprocate. Okay, so this can actually be written as 4 times K, and then times Q squared over L squared. So I think you guys can proceed up to here, because you know what your K is just equal to 1 over 4 pi epsilon naught. So you know how to evaluate this. And then your Q, I think you can actually leave it in terms of Q. You leave your final answer in terms of Q, because the Q has not been given, but then the L has been given as 0.2 meters. So you can put in all the numbers that you have, and then it's like in the question, if I'm not mistaken, in the question we have not been given the value of Q. So it means that this answer here, you must leave it in terms of Q. Any questions? So that is how this should be done. Any questions? Okay, so this is now the third question. Is it the third question from the tutorial sheet? No, I think this is not the third. This is actually there. The fourth question. What I'm looking for is the third question. So let me copy it. What I'm looking for is the third. Okay, so if I'm not mistaken, this is the third question that I have. Since you guys, it seems you are not in a very good mood to respond, so I'll just be talking, and then when you need to say something, you inform me. Okay, so we say that a semicircular rod of radius r is charged uniformly with a total charge of Q. Okay, with a total charge of Q, and then in this case, the Q, as you can see, is capital letters. Now, since this is a continuous charge distribution, so I would want to write it in terms of a capital letter. Since it's a point charge, it is a continuous charge distribution. Okay, so how can I work around? So what am I looking for? Find the electric field intensity at the center of curvature. So the important thing, first of all, is to draw the diagram just to see what is going on. So I have this, and then so this is the semicircular rod. This is the semicircular rod that I have here. I think let me increase. Okay, so this is the semicircular rod that I have. And then I have the center. This is the center of curvature that is here. Okay, and then I've been told that the radius of this thing is actually r. So the radius is r. I can just write. So that is the radius. And then the question is that I have to find the electric field intensity. I have to find the electric field intensity at the center. At the center. Okay, so what do I need to do? Now, this is slightly different from the questions that we have done so far because it involves continuous charge distribution. This is no longer a point charge. This is no longer a discrete charge distribution. It is now a continuous charge distribution. So as before, you see, we are going to assume that this entire configuration is actually made up of very, very, very small elements. An infinite number of infinitesimal elements, each of which has got a charge contribution of dq. All right. So what I'll do is that I'll assume that I'll only take an element, maybe that is there somewhere here. And then within this element, I'll say the length of this element is, I'll call it ds. You know, s is usually the symbol that is used for distance. And then I'll say that this element has got a charge that is dq. Now this charge is just a contribution to the entire charge, which amounts to Q. Okay. So, and then the other thing that I will do is this. The other thing that I will do is, let me just rub this. Okay, so I'll say that this angle here, I'll call it as d theta. don't confuse theta and Q. Maybe let me write Q more appropriately so that we don't confuse it with theta. You know, theta is the angle that this makes. So this, I must write it as Q. What I'm trying to say is that the angle, if this is your normal, this is 90 degrees. What we are saying is that from here up to here, we are calling it as theta. So this small angle that is here is just a small contribution to theta, which we are calling d theta. So what is the starting point? The starting point is, first of all, on the diagram, we know that due to this dq here, there will be a force that will be in this direction. There will be an electric field that will be in this direction, and we'll call this electric field as B, dE. Okay? This is the electric field just to this small element. But you know that there will always be another element that might be on this other side. There could be another element that is on this side, which is directly opposite to this guy. And then it will also produce another. It will also produce, okay, I'll repeat what I'm saying. What I'm saying is that this is a continuous charge distribution. So this element of charge is contributing to the electric field at this point. It is contributing dE. Okay, it means that you can always find a corresponding element on the other side, okay, which is contributing this much, the same, which is contributing the same amount of the electric field, but then in this direction. So why am I doing this? The reason why I'm doing this is to show you that if you resolve this like that, you know, these are vectors, so you can resolve this vector here, you can resolve it along the y-axis and along the x-axis. This vector here, you can also resolve it along the y-axis and along the x-axis. So you see that the x component will cancel out. So the x component will cancel out. So this is basically the symmetric argument that we are talking about. So in short, we are saying that the effective electric field will actually be equal to, it will actually be in the y-axis. Okay, the effective electric field will be in the y-axis because the x components will cancel out. The x components of the electric field will cancel out because due to symmetry. So Ex cancels due to symmetry. Okay, so now the question is, if this is your theta here, then this will also be your theta here. Then how can you express this, the electric field in the y direction? The electric field, how do you express the electric field in the y direction? By the way, it will be in the negative y, since you have your y as up. So it will be in the negative y because it will be down. So now my question is that since you have your theta here, then what will be this? What will be the y component? Then you can write the electric field must be equal to, before I write the electric field, you see, I'm just writing a contribution. So I must write D. Even here, I must write D since it is just a contribution. So I'll say in a similar way, I also must write here as okay, so this can be written as dE and then cos theta. Let's try to look at it carefully. You see this with respect to this angle, this is the opposite, and then this is the adjacent. The dE here is the hypotenuse. So you have the hypotenuse, and then you also have the adjacent. So this the trig ratio that you're using is the cosine. So try to just go through that and convince yourself that that is what we are supposed to have. Okay, so now let us proceed. So in short, we are saying that the dE, this is the effective, the effective electric field is what is this? This is just basically K, and then times dQ. Remember, this has got a charge of dQ, and then over what is the distance? The distance is R. So I'll say R squared, and then I'll say times cos theta. Mr. Mchemba, I've seen your hand. Mr. Mchemba, I've seen your hand.
Yes, sir. I just wanted to find out, sir. How about if we are maybe going to present your drawing, maybe that semi-circular rod?
Okay, I can barely get what you are saying. I don't know, maybe your headsets are not properly positioned. Say it again, and I can barely get what you're saying.
You're getting me, sir?
Try to increase the volume.
Sir.
Yes. Yeah.
Okay. I just want to find out, how about if you were to present your drawing, maybe, for example, that's a semicircular vertically, can you still get the same answer?
Yes, you'll be able to get the same answer. In fact, I would advise you to do that and see whether you're getting, you know, the answer would be, because the question has not restricted you on the orientation of the circle. Okay, you'll be able to get the same answer in terms of the magnitude, but the direction will be different. It will depend on how you are made. Circle. It can be upwards because the question has not restricted you. Okay?
Oh, all right, sir.
Okay. So what is the next thing? I think I'm now running out of time before the end of the session. What is the next thing to do? We have to express this dQ in terms of a certain charge density. What charge density are we going to use? Is it linear or area or whatever? So you can see, since this is a line, we are going to use the linear charge density. So you can see that dQ is basically linear charge density times ds. That's what we learned. You see, ds is the length of this, so the dq will just be given by that. Okay, and then there's also another thing that we can do. This ds here, this ds, you can see that it is a variable. Maybe let me write this: de effective is equal to k, and then times lambda times ds, and then over r squared, and then cos theta. How many variables do you have? You know, k is not a variable, it's a constant. R is also a constant because it is the radius of this semicircle. But then ds is a variable. ds is a variable because you could take this element at any point that you wish. And then theta is also a variable because as you are changing the position of ds, then the theta is also changing. So you have two variables, so you only want to have one variable. So you must have a relationship. What is the relationship between s and the theta? If you inspect this diagram very, very well, you inspect it very well, then you realize that you have this relationship. Tan theta can actually be written as, tan theta can be written as the ds, the opposite, and then over the adjacent, which is r. Okay, so when theta is very small, so I'll say that for very small theta, from your mathematics, you know that if theta is very small, then tan theta will approximately be equal to theta. By the way, I must write d theta here because I'm looking at this ds. So I must write this d theta that is here. Okay, so for very small theta, this is a mathematical equation or a mathematical identity that you have. Tan theta is approximately equal to theta. So where there is tan theta, I can actually, where there is tan d theta, I can put d theta. If this d theta is very, very small. Okay, so it means that this equation here, how can I write it? I can write it as theta is equal to, theta is equal, I can write it as d theta is equal to ds over r, which implies that this ds can be written as r d theta. Okay, so remember the equation that I have is this one here. This I can call it my equation 1. And then this one I can call it my equation 2. So if I substitute this, if I substitute equation 2 into equation 1, okay, it means that I'll have, remember equation 1, just to remind myself, it is looking like this. So I have my k, I have my lambda, and then where there is ds, I'm writing this r, and then d theta, and then remember there is an r squared at the bottom, and then there is a cos theta, if I'm not mistaken, is the cos theta. Okay, so from there you can see that this r can cancel with one of the r's there. And then if you inspect this equation, everything else is a constant. Everything is else is a constant apart from just the theta. So I can now integrate. So if I integrate on the left-hand side, then I just have the electric field, the total electric field. On the left, this is on the left-hand side, I have the electric field. On the right-hand side, I have K, then and that, and then over R, and then I have cos theta, d theta is the one that I'm actually integrating. What are the limits of this integrate? What are the limits of this integration? It means that my theta here, my theta can vary from minus pi over 2. Remember, this is the minus side, so it is 90 degrees, so it's minus pi over 2 to pi over 2. So these are the limits for my theta. So I'll have a minus pi over 2 and then up to pi over 2 positive. Okay, so this is a very simple integral. I'm sure you know what it evaluates to. So I have k lambda over r, and then if I integrate sine, if I integrate cosine, I think I'm going to have a sine. I'm going to have sine theta, and then minus pi over 2, and then pi over 2. Okay, I'll leave it for you now to go through the steps step by step. If you evaluate this, okay, let us do together over r. And then what is sine? Sine pi over 2, you realize it is nothing but 1. And then minus the sine of the minus pi over 2 will just give you minus 1. So in short, this can this gives you a plus. So it just goes down to that over r. Okay. So we are almost now zeroing in. We are almost winding up. So what is your lambda? So we are saying that the E effective is just equal to 2k lambda over r. That is what this equation is telling us. So now you know that your k is equal to 1 over 4 pi epsilon naught. And what is your lambda? This is the linear charge density. So linear charge density is just basically the charge per unit length. So we have the charge, and then what is the total length of a semicircle? It is basically pi times r. This is there. You remember the full circle is 2 pi r. That means the half circle will just be pi r. So if I substitute all this, then I have the effective. It will just be equal to 2 times 1 over 4 pi epsilon naught, and then times this q over pi r. Okay, so you see here cancels, it becomes 2. So the effective electric field will just be given by q over 2 pi squared epsilon r. So this is actually the expression for the electric field at the center. So as long as you have the charge and you also know the radius, by the way, this radius must be squared because you have this and that, so it must also be squared. So that is basically the expression that you get to. Any questions? Any questions?
Can send the recording if you can.
Okay, so
you just send the recordings for us.
I think we are done with this. I can stop this session, and then in the next session maybe I'll just help you to solve one question, and then the rest of the questions will be now for you guys to do them on your own. Okay, so let us proceed. You see, so far we have done some questions on point charges, which is a discrete charge distribution. I've also demonstrated to you how you solve problems to do with continuous charge distribution. Now, I just wanted to also do one question just to show you how you work out questions on Gauss Flux theorem. So I've chosen question 6 from the tutorial sheet. Guys, when you see the Q, you think that it is charge. So I'm not saying that charge 6, I'm saying question 6. In this case, so it is question 6 from your tutorial sheet. So the question reads, consider a charge Q distributed through a sphere of radius r with a volume charge density, which is given by rho is equal to A, and then in brackets r minus r, coulombs per cubic meters, where r is between 0 and capital letter R. So the question is use Gauss Flux theorem to calculate one, this is part A, the electric field supposed to be the electric field at a point inside the sphere. So it's supposed to read the electric field at a point inside the sphere. And then the second one is supposed to be find the electric field outside the sphere. Okay, so let me just try to draw the situation. Now, maybe before I even do that, this kind of charge density, we have been told that it is the volume charge density. Do you think that it is uniform or it is non-uniform? This kind of charge distribution, is it uniform or non-uniform?
It's non-uniform.
It is non-uniform. Why do you say so? Why do you say so? Okay, what do others think? I think I'm very interested in the answer to that question. Is this charge distribution uniform or non-uniform? What do others think?
Also, it's uniform because the charge is distributed over the volume. So meaning if we consider it as a charge at the center, then it will be distributed for same volume. So it's uniform.
You didn't get the reasoning. The reasoning is that if the charge is what? Just go through your explanation again. Okay, so in short, to just help you, you can see that this distribution, the charge density is a function of R. So it means that at any given radius, so this is the volume charge density is a function of R. Remember, R is the radius. So what it means is that, for instance, what do you think would be the what? What do you think would be the charge at the center? Just as an example, what do you think would be the charge density at the center? So at the center, what is R? At the center, what is R? I think I will not accept this. What is R at the center of the sphere?
0.
0, sir.
0, yes. So why are we delaying? So R at the center is equal to 0. So it means that there at the center, to have a value of A times R, since this will be 0. So it will just be AR. And then what about at the surface of the sphere? So what about at surface? About the surface of the sphere? What will be the charge density when R is equal to R? Okay, so it means that where there is small letter r, you substitute capital letter R. Because you know at the surface, it means that this small letter r, it will become just equal to the capital letter R, which is the radius of that sphere. So it means that the density will be equal to 0 because this R minus R will be 0. So it shows you that this is a non-uniform charge distribution. It means that the charge, the highest, it has the highest density at the center. And as you go outward, then the density is reducing until finally, when you reach the surface of the sphere, there is actually no charge because the charge density there is equal to 0. Are we together? That is the first thing. The next thing, what do you think? Do you think that this is a conductor or a non-conductor? We haven't yet started answering the problem, but we're just trying to analyze it from different perspectives. Because if you understand the question, even if the question is changed, you will still be able to solve it because you understand the new conditions of the question. So if you look at this question, do you think that this sphere is a conducting sphere or a non-conducting sphere?
So I think it's a non-conducting sphere.
It's a non-conducting sphere. Why do you think so?
Because on a conducting sphere, if you press a charge at the center, it's distributed uniformly at the surface.
Exactly. So this should be a non-conducting sphere because you can see that just given by the way the charge is distributed, it means that the charge is distributed within the bulk of that sphere. The charge, you know, if the sphere was a conductor, then you would not expect to have the charge inside. You would expect all the charges to be at the surface. So these are some of the simple things that you must that are useful when you are dealing with these things. Okay. So I'll wrap this. I was just trying to shed more light on the question. Okay, so we are saying that inside the sphere, see this part A of the problem is talking about inside the sphere. So it wants us to calculate. So it means that the R must be less than the capital letter R. Remember, capital letter R is the volume of this sphere. So in short, we are saying that we have, you pardon my drawing, it will not be very good, but I think I can still draw a better one. Okay, so this is your R. So the question says that find the electric field at a point inside. So it means that I must think of it, I must draw a Gaussian surface. The Gaussian surface that I must draw must be inside. It must be of radius r, small letter r, and then it must also be inside. So I draw there. This is a very bad sequence. Can I do better than this? So I've drawn the diagram. I've drawn the diagram as if it is a circle, but you must have it in mind that this is a sphere, it's not a circle. So basically this is the sphere itself. And then what I've drawn inside here is the Gaussian surface. You remember when drawing the Gaussian surface, you draw the Gaussian surface in such a way that it is at the point where you want to find the electric field. Since I want to find the electric field inside the sphere, then I've drawn this Gaussian surface inside the sphere. Okay, so the next thing is that I'll apply Gauss Flux theorem. What does Gauss Flux theorem tell me? It tells me that the flux, Gauss Flux theorem tells me that the flux, the electric flux, must be equal to the charge that is enclosed in the Gaussian surface over epsilon naught, if you remember very well. So we say that what is the flux? The flux is given by this integral. It's called the surface integral. Okay, so you're saying that this must be equal to the charge enclosed over epsilon naught. Now this charge enclosed is the charge enclosed by the Gaussian surface. So in our diagram, this is the Gaussian surface. Okay. So where do we start from? You know that the left-hand side, let us start from the left-hand side. So the left-hand side says that we have this how can we write it? We can write it as E, and then the A, and then cos theta. I'm just going through the steps which we all know. What is the theta in this case? Remember, theta is the angle between the electric field and the area vector. So what is the theta in this case? Can someone tell me? What is the theta?
Equal to 0.
the theta is equal to 0 because you see that the electric field and the area are in the same direction. I think I will not do a lot of explanations there because we have done it a lot in class. So since the theta is equal to 0, then it implies that your cos 0 is just nothing but 1. So you can write, what I'm writing there is basically this. So I'm saying that this, the flux, I'm saying that the flux is equal to this electric field. I can factor it out because it is a constant. So I'll just remain with dA. Okay, so if I integrate the dA, then what I just have is E times A. Now you must understand this A is nothing but the surface area of the Gaussian surface. In this case, what is the Gaussian surface? It is a sphere. It's a sphere of radius that. So I'm saying that the flux, the electric flux, will just be given by this electric field times what is the surface area of a sphere? It's just 4 pi r squared. So this is basically the surface area of the Gaussian surface. So in doing that, I have worked with the left-hand side of Gaussian flux theorem. Okay, so now what about, by the way, I'll say this is my equation 1, and then I'll say this is my equation 2. Now I will deal with the right-hand side of Gauss flux theorem. You see, if you look at the right-hand side properly, I just need to work out what is the charge that is enclosed. Remember, this is the charge that is enclosed by the Gaussian surface. What is the charge that is enclosed in here? So how do I do it? How I do it is that, first of all, I can say that the charge, is just equal to rho times dV. I know that, I hope that all of us are happy with this. Remember, this is volume charge density. So volume charge density is just equal to the charge and then over volume. And then this is the charge. I'll integrate it within appropriate limits in order for me to get the charge that is enclosed. This charge that is enclosed in here. The charge that is enclosed in here. Okay. So now, in the question, I think I've been given this row. This row in the question, it was given as what? As A, and then R minus R, if I'm not mistaken. Okay. And then, you know that this is a sphere that we are talking about. So the volume of a sphere is given by 4 over 3, actually. The volume of a sphere is given by 4 over 3, and then pi r cubed. So it means that from this volume, I can actually find dV. What is dV? So it implies that this dV, I'm differentiating this with respect to r, then it will dV over dr will be equal to 4 over 3. Then pi, I'm differentiating this guy. What does it become? It becomes 3 r squared. Okay, so this can cancel out with that. So I say that the dV can just be given as 4 pi r squared dr. So it simply means that here where there is rho, I have an expression for rho. Here where there is dV, I can now write this expression for dV, which is 4 pi r squared dr. So it means that this dq, it will just be equal to A times r minus r, and then where there is dV, I put 4 pi r squared, then dr. So so we are making progress. Now you can inspect this equation. You know, A is a constant, R is a constant, 4 pi is a constant. So the only variable that we have is this small letter R. So it means that you can actually be able to integrate. Okay, so you're integrating in order for you to find the total charge that is contained here. Okay, so before we proceed, I can ask the question, what do you think is the lower limit for R? What is the smallest value that R can have? We have said that this R is a variable because this Gaussian surface, you could draw it at any point as long as you're inside the sphere. So what is the smallest value that R can assume? What is the value? What is the smallest value that R can assume?
0.
0. So the lower limit for R will be equal to 0. The upper limit will be R itself. Upper limit will be R itself. So I'm now going to integrate. Okay, so you have this integral. So you have Q is 4 pi A, then integral 0 up to R. If you like, you can say that this is R squared times R. I'm just distributing this R squared, then minus R to the power 3, then everything. Okay, so what method of integration can you use? You can use polynomial integration. You know, this is a polynomial of order 2. This is also a polynomial of order 3. So you can actually use polynomial integration. So this Q can be written as 4 pi A. And then if I integrate this, then what I just have is, you see when you're integrating, then you add 1 to the power, and then you divide that number. So I have R 3, and then to the power 3 minus R 4 over 4. And then I'll say 0 up to R. Okay, so this Q will just now be given by 4 pi A. Okay, and then you see when I substitute the lower limit, everything will be equal to 0. So I'm only interested in the upper limit. So it will just be equal to R 3R over 3 minus R4 over 4. If you want, you can write it even in a better way to say that this is 4 pi times A. You can factor out R3 so that you just remain with R over 3 and then R over 4. So basically this here gives you the charge that is enclosed. The charge that is enclosed within the what? charge that is enclosed within this Gaussian surface. Okay, so it means that you can now go to your left-hand side. You can go to your right-hand side. Remember, we are looking at equation 1. We have already evaluated the right-hand side of equation 1. We are trying to evaluate the left-hand side. Sorry, we have already evaluated the left-hand side. We are trying to look at the right-hand side. So we have now calculated this. So it simply means that, okay, so now I have to look at this. See, this was my equation 1, which is basically Gaussian theorem. So the left-hand side of that equation, I found it to be equal to this equation 2, right? And then the right-hand side of that equation, I've now found it to be equal to that. So I just now have to equate those. So there, I think I had the electric field, that is equation 2 times 4 pi r squared was equal to, now this is the right, this is the right-hand side, which is now 4 pi a, and then r3 over epsilon naught, and then times r over 3 minus r over 4. So remember, I want to make the electric field subject to the formula, but then I can see that this can cancel out with that. And then, this entire thing can cancel out so that I only remain with 1 there. So it means that the electric field now, as you can see, it will just be given by A times R, I think over epsilon naught. Just look at it carefully. So we have A and then R over epsilon. And then we have R over 3 minus R over 4. Okay, so this is basically there. Okay, sorry, ladies and gentlemen, let me just
Sir, your mic is muted.
Sir, let me get what you are saying. Mic is not clear.
Okay, hello? Hello?
Oh,
Okay, so I'm sorry that I think something came up that needed my attention. Okay, so basically this is the expression that you get for the electric field. So as long, now you have this constant A that you have to evaluate. What is this constant A? Okay, so you know your R. Your R is basically the distance from the center up to the point where you want to find the electric field. This capital R is basically the radius of the sphere. So now how can you compute this A? How can you compute this A? It is also very simple, because from this expression, from equation 3, okay, maybe let me just call this as equation, let me call this as equation 4. Okay, so from equation 4, what is the electric field? What is the electric field? Okay, so which equation can I use? So what did we say about the charge at the surface? What did we say about the charge at the surface? Huh? Hello? Are you guys able to get me? Hello? Hello, class? Are you able to get me?
Yes, I was getting it.
Let's proceed. So we are saying that this electric field, what is the electric field when R is equal to R? At the surface of the sphere, this small letter R is equal to capital letter R. So from equation 4, it means that wherever there was small letter R, I can put a capital letter R there in order for me to find the electric field at the surface of the sphere. Okay, so what does that give me? So it will give me something like this. It will give me something like this. And okay, so are we all together up to this point? I think I'm just using this in essence, I've already found my answer here, but then I'm just trying to find what constant, how can I express this constant in terms of the other parameters that have been given. Okay, so it means that this electric field, as you can see, it is a function of R. It means that at any given R, I can find the electric field. So now what about at the surface of the sphere? At the surface of the sphere, I know that R must be equal to R. So it simply means that when I substitute this capital letter R here, then I get this expression that you find here. If I simplify it, then you can actually make a subject of the formula in this equation. Then you'll be able to express this constant A in terms of R. I think we'll end here. I think we'll end here for the day, and then we'll pick it up when we meet next time.